are ready. So it's my great pleasure to introduce Chenlong Wang, who is a PhD student, final year at the University of Washington. Co-advised by many people, Ishiel, Alvin, Amy, and myself, many different collaborators on a range of topics roughly in visualization and data science computations. And today he'll talk about authoring visualization, but perhaps more about the algorithm that drives this application. Thank you, Chenlong, for joining us.
Yeah, thanks for the introduction. So hello, everyone. I'm Chenlong from University of Washington. And today I'm going to talk about how to synthesize visualizations from examples. So just a briefly introduction of what is visualization from a formal perspective. So a modern way to formalize visualization is as mappings from data column to geometric properties. This is something formalized as grammar of graphics. You may have never heard of the term, but it has been the power horse behind many modern visualization tools that some of you have already used. So what does this formalization mean? It means that when you want to create a data visualization, you can specify them as mappings. Now we have an example data with two columns, group and value. If we want to create a bar chart that shows for each group, use a height to show its value, we can define this as a function named by mapping the group column to x positions of bars and mapping values columns to heights of the bars. And what we can get is a bar chart. As you can see here, this mapping is able to map each row into a bar in the bar chart. So in general, this is a powerful way of defining visualization and has generally made visualization very easy. But in practice, is it always so easy to create a visualization? Let me use a slightly more complex example to show here. So now instead, we have a data set with 4 columns, and we want to show for sum of each group and for each column into a stack bar chart. So here, as you can see, what we want to do is that for group 1 and for column A, we want to create a bar. The height is basically a summation of value 0 plus 1 in the column. So as you can see, this visualization is basically one step from our basic bar chart, but it's no longer clear how we are able to use a simple mappings from data columns to geometrics in order to define the visualization. And in fact, it is not possible to specify in this way. So in this particular example, because the visualization expects an input data with 3 columns, that one map to X, one map to height, and one map to color. And it turned out in this case, because there is a mismatch between the input data layout and the visualization design, we cannot easily specify it as mappings. So as a result, in practice, what we need to do is to go through a data transformation process. So in this particular example, what we need to do is to first transform the data with an operator called gather. What this gather do is basically transpose the table so that column ABC becomes values in a key column, and their corresponding values are in the value column. And after this transformation, as you can see, this weird region is basically able to turn into a rectangle region. And after that, we still need to go do one more step data transformation. That is to aggregate the data for each group and for each key in order to calculate the sum. So here it's kind of clear, like basically for group 1 and column A, we're able to calculate the summation by summing up the values in the val column. And after all this data transformation, it's very easy on how we specify the visualization, right? We can basically map group column to X positions, key column to color, and values to height, and then we get a stack bar chart, as you can see, as intended. But of course, as you can see here, all this step of data transformation has bring a barrier of visualization authoring. And this can be something challenging for experienced user already, and then it's maybe even harder for beginner users as identified by prior studies. So the question here we are trying to solve is essentially, can we leverage program synthesis to help those people to make it easy to author visualizations, essentially bypassing those data transformation challenge? So basically, motivated by the fact that many end users is able to communicate visualization ideas using partial visualizations. So essentially, those people typically, when they're asking for help, they create a sketch, a partial visualization to demonstrate how they want to visualize a few data points in the data set. and they're asking the expert to try to generalize that to the full data set. So based on this observation, we are able to see that if we allow users to illustrate visualization ideas using partial visualizations, we can potentially allow them to bypass this visualization specification challenge. And with this motivation, we create a design is a paradigm named visualization by example. So essentially, given an input data set, instead of asking user to specify transformation and visualization programs, we ask them to demonstrate visualizations using examples. So in this case, as you can see, the user demonstrate how they want to map the first few rows into the data set as 2 example bars. And what they're essentially asking experts help is to say, can you generalize this example to visualize a full data set as a full visualization? As you can see, this design is basically able to inherit the simplicity of visualization specification using those simple mappings. But there is also a bonus that this approach is also data layout independent, meaning that even if users have a completely different input layout, they can use the exact same example to demonstrate the visualization idea. So this is ideal for end users. It's a way to easily specify visualization, and this specification is data layout independent. So they don't need to worry about anything about data transformation. Of course, as you can see, we make it easy for users, but we make it harder for computers because we need to have our algorithms that is able to generalize user example into programs that can visualize a full data set. And now let's look at the algorithm perspective of this problem. How can we have computers to solve this task? So let's take a look, what does our machine need to do? So starting from the user input is input data T and the partial visualization. What we essentially want is to have our computer to first synthesize the data transformation program PT to transform the data, and then a visualization program PV that is able to map the transformed data to a visualization. And the requirement here is that the synthesized visualization should contain all elements demonstrated by the user. So a recapitulation is basically we want to synthesize 2 programs, PT and PV, such that when applied on the input data, the output will contain everything demonstrated by the user. So one thing you can see here is that we need to solve a 2 synthesis problem at once. Essentially, we want to synthesize those 2 programs from 2 languages. So how can we solve this? So generally, our approach is to use a decomposition synthesis approach. We go through this problem backwardly. So we're starting from this partial visualization. We first decompile the visualization with a visualization decompiler. That is basically able to infer the visualization program directly from the plot. And then from there to decide an intermediate table is basically a small table that is in control of the partial visualization. And then, of course, the second step is to synthesize a data transformation program such that we can turn the input table to be an output that is able to contain the intermediate table. This is basically a contract of the 2 different parts of the algorithm. The one part is asking, if you can help me find this intermediate table, I can solve the visualization for you. And now the problem is basically, how can we find this data transformation? So because of time limit, I'm not going to talk too much on how we can design a language to make this decompiler easy. But today, instead, we're going to focus on this data transformation synthesis problem. So the problem here, right, is basically we want to synthesize a program PT such that we can transform the input data T to contain the intermediate table T star. So this is our formal problem statement here. And the general way to solve this problem is to search the programs over the search space. This is basically a program space defined by the all possible data transformation defined by this language operators. And to solve this problem, the general idea is to do the search. We can start with nothing, and then we can enumerate program sketches. And those program sketches are basically programs with uninfilled parameters with holes. And then what we can do is to iteratively fill these holes based on the language operators. So for example, we can enumerate what are possible values to fill in each hole. And whenever we have a concrete program, we can check it against our objective. If it is incorrect, we can continue search on other branch. and then we do more check, we do more search, and then we do more check until we are able to find a program that satisfies our objective. So here, as you can see, problem solved. But the only problem is that I didn't tell you how much time it takes to solve this problem right now, because even for this small problem, there is a huge number of programs to visit. And this number will grow exponentially with the number of columns we input as number of instructions. This is because we're tackling a very challenging combinatorial program search problem. So the key thing is about how can we make this process tractable. So a typical way, like adopted in the past 5 years of program synthesis research, is to use an approach called deductive reasoning. So general idea is that instead of wait until the very end to check whether a program is satisfiable, we can reason about those partial programs. So for example, we can take a look at this program filter without any predicate field yet. So now we can check basically, as you can see, filter will only remove some rows from the table, so it will not change the number of columns in the input. And thus the output should have column number 4. But according to our requirement, the actual output has column number 3. And then there is a contradiction. So we can prune this program away immediately, avoiding searching this branch. So as you can see, this approach allows us to prune program without having to instantiate those unrealizable part of the search space. But as you can see, we're not so lucky, because if we're able to consider both filter and projection is essentially remove some column from the input, then we are not able to derive any conflict, because we can only conclude that output column number is smaller or equal to 4, and there is no contradiction. So what is the problem here? Is this problem wrong? So actually, if you think about this, our idea is not wrong. We want to prune those search space as early as possible. But we are having a fundamental problem here is that using only those high-level information, we cannot precisely capture the semantics of those partial programs, and thus we're losing a lot of pruning opportunities. So based on this observation, we made our design is basically a new approach of reasoning those partial programs based on abstract semantics by propagating concrete values through partial programs. So let me use an example to show you. So remember this program with filter and projection, right? We cannot do anything about that using only like column number. But what we can do is to reason about that in a more concrete way using values. So let's take a look. So this T-out is an output program. Do we know nothing about this program? Actually, no, because one thing we can know for sure is that whatever predicate or whatever parameters we're going to supply, this output program would be a table that is included by T. By inclusion here, I mean a generalized version of containment, basically consider both column and row containment. So this essentially is an abstract property of all this family of programs. So whatever instantiation of the parameter, this property must hold. And this is essentially abstract semantic of this program. So this property basically over approximation of the program out behavior that allow us to capture the behavior of all programs in this branch. So now we instantiate this property with our input and output example. Then we can see it requires this small table to be contained by this bigger table. But as you can see, there is a contradiction because apparently there is no way to derive this containment relation. And in this way, we're able to prune those program away. But using the same approach, we're able to actually prune a lot of other programs away at the same time. And then in this particular case, we're able to reduce the search space by 84%. So in general, as a kind of quick summary, this approach is allow us to reason about program semantics by propagating those concrete value through partial programs that allow us to approximate behavior to analyze the programs. So and we define this inductively on all program operators so that we can analyze those partial programs to explore those pruning opportunities. So basically, this is how we solve the visualization problem. Starting from the partial visualization, we basically decompose a task with a visualization decompilation, and then we use this value-based abstraction to scale up the combinatorial program search. So as an evaluation to understand how well it works in practice, we evaluate with a practical library with basically R tidyverse and the visualization library Vega Lite, which collect 83 benchmarks about visualization people have online and use a sampled visualization to to test efficiency of their algorithm. So as you can see here, this is a result that shows the number of benchmarks can be solved within a given time limit. The x-axis, the log scale, shows a time limit for each benchmark. Y-axis shows the number of benchmarks. As you can see, Phelps is able to solve 90% of those tasks. And in particular, we're able to solve a majority of them within a few seconds. And this is crucial for our practical use of the tool in an interactive setting. And if we compare this, actually, when we look at those unsolved cases, there's one case actually timeout due to complexity, and several cases due to unsupported operators. That is basically beyond those relational transformations. So when we compare this against our baseline, this blue line shows a case without the value-based abstraction I mentioned earlier. And the brown line shows a case basically using a naive search earlier. As you can see, decomposition is actually quite important, but it's not itself is not sufficient. It's only when we're adding those abstract-based reasoning, we're able to scale up a lot more. And in particular, the speed that we obtain is 59 times. It means that sometimes users need to wait for a few minutes, now can just be solved in a few seconds. Of course, there's still some opportunity about like leverage learning to search or multimodal synthesis to solve those slower cases, but this is something that we can discuss later. So in general, today I cover this synthesis problem, especially on how to apply value-based abstraction to analyze behaviors of partial programs. Something I didn't cover here, including how we design the language to make this decompilation easy, like earlier. And another thing is basically, this is something you can see in our POPO paper. And another thing is basically how do we actually build an interaction model to support some practical use problem about how to create examples and how to handle ambiguity from the user. So this is something we built in our Kai paper. And also you can take a look at the tool in our website to see like how it actually works in practice. So with this, this is basically it, and I'm happy to answer any questions.
Thank you, Chenlong. Other questions from the audience? Type them in the chat. So Chenlong, do you have an example where you actually compute the abstract semantics on some partial program in terms of an input table so that we can see what the output is, so the one that preserves the input values?
Yeah, so this particular example is actually kind of an interesting case, right? It's basically this property that if we evaluate this program concretely, we're going to require some concrete predicate and concrete parameters. And if we evaluate abstractly, we just get an upper bound of the result, which is essentially the input table. It means that any possible output will be contained by this input. And for this particular case, this is the abstract output. So yeah, so in general, the reasoning is basically allow us to summarize behaviors of all programs with all possible like parameters in this case. Yeah.
So there is an interplay with the language design, presumably, right?
Right. I think it mostly comes into the abstraction design. You can see like using those type information is more abstract and cheaper, and using those value-based abstraction is basically grant you more pruning power, but also relatively more expensive in terms of checking. I think there are different design for different language, different scenarios as well.
Mm-hmm. Mm-hmm. Thank you, Chenlong. I think we can switch now to Bill.